Okay, we are going to continue our scaling journey. Today's a bit of a grab bag of stuff. I mean, we're really going to talk about some of the more advanced details of scaling laws and how we scale up models. And in doing so, we're going to cover what I feel like are some important details in how you would scale up a language model in practice. Okay. So, we might want to ask some questions, like, is the scaling law stuff that you talked about 2 lectures ago, does that actually work at real building open source model scales? It would be nice if we could optimize some of this. There's a lot of learning rate tricks and other things that people do that I think you should know as people that are informed about how to build a language model. So we'll talk about some of these optimization details. And then I think the last thing I want to talk about is when we scale up, there are certain things that are going to be a little bit trickier to tune. We know that optimizers and optimizer behavior is going to be actually pretty scale sensitive. And because of that, things like initializations, learning rates, batch size, those we need to carefully think about as a function of scale. So we will talk about how to think about those carefully. Okay. So up until now, most of our discussions, what I would call the classical, scaling laws canon. We talked about Kaplan, we talked about even Hessness, and then the Chinchilla paper, right? So we're up to date with 2022 or something. Since then, there have been a number of scaling papers that are published by people who train big models. Although I think the number of such papers have decreased in recent years, and most of them have come out of the open source community in China. And so today I want to talk about a number of these that I've sort of curated and selected to give you a sense of what does scaling at the frontier, at least open frontier, look like? What are the things that these people care about or worry about? And what would you need to do to sort of speed run your way from Chinchilla all the way to, let's say, Kimi K2, most recent release that has some scaling details. Okay, so that's going to be the first part of this lecture. We're going to go through a couple papers and we're going to go through the details. The second part is going to be a discussion of optimizers and initializations. And remember, I spent a non-trivial amount of time 2 lectures ago on the selection of batch sizes. That's going to be an important factor, and it's also going to be important thinking about how we're going to tune things like learning rates. Those are very sensitive, very important to get right. And so it turns out that a lot of effort has been invested into getting those things right, and we will talk about some of the techniques to do so. And this may, in fact, even be useful in your day-to-day lives of training various language models, because they'll give you a sense of how to change your hyperparameters in your experiments as you scale up or down. Okay, so I'm going to spend a non-trivial amount of time talking about 2 papers in particular. They're not the newest papers. They're not necessarily the most, actually DeepSeek one might be one of the more detailed ones. Most detailed scaling paper in general, but I think this hits a sweet spot. So both of these papers are kind of serious scaling investigations from people who build reasonably high performance models. And importantly, they take pretty different approaches to some of the key questions that we will ask today. And so I think they're a good way to motivate a lot of the rest of the lecture. So I'm going to talk about these 2. First one's Mini CPM. This was, I think, back in 2024, high performance small language model. And DeepSeek, you all are now familiar with this. I no longer have to justify why I'm talking about DeepSeek, which is great. We'll start by talking about Mini CPM, though. I do like this paper, especially when it first came out. It felt very fresh and new and very, at the cutting edge. Even in 2026, I feel like a lot of the things that the Mini CPM folks did is very informative to us. I'll talk about this later as I get to the newer papers. But I think it's kind of becoming the case that a lot of this classic scaling stuff, like how you set learning rates, how do you do Chinchilla, those kinds of things I think are now taken for granted. Everyone just assumes that you know how to do those things. And so people don't really talk about those as much anymore in the paper. So it's really nice to talk about some of these older papers for that reason. Okay. So Mini CPM is an effort by a bunch of industry, academic partnerships folks over in the Chinese open source community to come up with a high performance, small-ish language model. And at the time when this came out, it was basically state-of-the-art for the 1 to 2 billion parameter bracket. Nowadays, Gemma and other models, and other models at 2B or 3B are going to be higher performance, but these are competitive, well-trained models, at least at 2024 standards. So how do you train these models? Okay, as I said before, we have to get some of these like scaling parameters right. And one of the things that I'll talk about today, that I'll emphasize quite a bit, is initializations are very important. Initializations are important because they allow you to make certain hyperparameters less scale dependent. So the first technique that I want to talk about from this mini CPM paper is a special class of initializations called mu-p. So mu-p, the whole point of this approach is to say, I want to make sure that my optimal learning rate is the same as I scale up and down, right? I talked about this very briefly in the 2 lectures ago, so you should hopefully remember that a little bit. But this is kind of the first real instantiation that we're going to talk about. What does that look like specifically? The mini CPM paper has a nice list of things to do. So they scale the embedding output. They scale the residual connections by the square root of the number of layers. They scale the initialization of all of their matrix-shaped tensors by the fan-in, fan-out ratio. They scale the learning rates of tensors, and you should pay attention to this one because this is exotic if you aren't used to like per parameter learning rates. And then they also scale the LM heads. We'll talk about why you do these things or like how you derive this particular set of scalings. Suffice to say that you're just going to change up how you're going to do your initializations and your learning rates a little bit in the hopes of stabilizing your learning rates a little bit. And of course, we're training a small model here, but we're still wanting to do a nice scaling strategy, right? Like part of the point of this study is not that you want to brute force, a 1.5B model like training hundreds of them. You want to get the hyperparameters exactly right the first time, so you're going to train a bunch of much smaller models and then get a scaling ladder up all the way to your target size of 5x or so, right? And so there's about a 5x gap between the biggest model they train on their ladder and the actual model that they're going to finally release, right? And their goal is going to be to nail down, I think, what most people consider to be the sensitive parameters, like optimal batch size, learning rate, and then the token to size ratio that we talked about at Chinchilla. They sort of also want to replicate a Chinchilla analysis. Much less important to us now and probably to you even if you're training, but I'm going to talk about it regardless because there's one important thing in the way they do that that I think is very informative and useful. Okay, so as I said earlier, right, the whole point of going through this weird initialization or non-standard initialization called mu-p is to try to make the optimal learning rate stable. Is it? At least in sort of the mini CPM case, the answer is yes. In fact, it's very, very clean in their experiments. They sweep learning rate across a variety of models, so each line is a model size. The minimal loss is basically right on 10 to the negative 2. I guess the minima slightly shifted for the smallest model, but I mean, even then it's quite close to the minimum. So this is a nice success case of the mu-p approach. We will talk about several other models and other papers that use mu-p. This is not the only way to do it, but this is one effective way to do it. And if you can get something like this, now you've kind of removed the need to tune the learning rate. But of course, even if you have a nice parameterization that fixes your learning rate to a single sort of optimum, your optimal batch size is still not going to be kind of the same. So the batch size actually varies as a function of both data set size and model size. So in their case, they run these sort of model training runs. So each column of points that you see on these plots is a training run. So they have a fixed batch size, and they increase the number of tokens processed, I guess from bottom to top. And then they ask, okay, we've done many of these training runs. What is the optimal batch size fitting sort of these quadratic sort of curves onto each of these sort of lines over here, this sort of equal loss contour? What they find is sort of this kind of optimal batch size scaling as a function of the number of tokens processed. And they do this across different model sizes. Maybe you would not be surprised by this, given the nice scalings that we saw in the Kaplan paper for critical batch sizes. But the optimal batch size does have a sort of power loss structure with respect to the target loss. And so we kind of see exactly the Kaplan style analysis of, if your loss is lower on the left, your batch size should be bigger, right? Critical batch size scaling. And so now given a particular loss target, which you can back out from the scaling laws, you can basically set what the optimal or critical batch size is that would give you the best trade-offs, right? So there's a nice clean trend here. This will let you set batch size very easily and precisely. Okay. So those two, the batch size and the learning rate scaling, they're going to come back over and over again. Those are arguably the most important and sensitive parameters to do scaling laws on. But I'll talk about one last thing in the mini CPM paper that I think is important. So remember, like to do chinchilla, right, we need to train a lot of different models. So we're going to, let's say, do isoflops. That means I'm going to fix a flops budget, and I'm going to vary my trade-offs between number of tokens and model size. And to do that, I'm going to, let's say, increase the amount of data I train on, right? So I increase the number of sequences. But as I increase the number of sequences, remember that each one of these gets a different learning rate schedule, right? You're all training on cosine learning rates. Cosine learning rates look different. You need to know the terminal sort of total budget before you train in order to have a cosine schedule, right? And so this leads to kind of a annoying fact, which is that you just need to keep retraining your models. If you want to train a 8 million sequence model, right, you can't restart from the end of a 4 million sequence model, right? You have to just restart from scratch because your learning rate schedule is just fundamentally different, right? And this is just very annoying. It's like a quadratic cost in some sense of doing this because you have to keep restarting your runs just from the start. And this seems very wasteful, and I think lots of other people did too. And I think one of the nice solutions from the mini CPM paper is what's now called, I think, the warm-up stable decay learning rate, or this is the popular term for this. And it's basically a big trapezoid. So you've got a warm-up phase. The warm-up phase is usually defined as a constant number of steps, not as a fraction of your training target, right? So this is independent of your training horizon. You've got a fairly long run where you're holding the learning rates constant. That's the stable phase. And then at the end, you're going to decay fairly rapidly down to 0, right? That's the decay phase. And generally, the decay phase is something like 10 to 20% of your total training run, right? So you're going to be stable for the vast majority of your training run, and then do a very rapid decay down to usually about 10% of your maximum learning rate at the very end here. And that's like a very typical warm-up stable decay learning rate. Okay, and why do we do this? What's the point of doing this? Well, we do WSD because now we can restart a run at any point at the end of the stable phase, right? So if I want to reuse a run and train it for longer, right, I'll just roll back my training to the last stable checkpoint, and then I'll just run the stable learning rates forward and then redecay the model down to 0, right? So this provides a very easy way for us to essentially run sort of scale in data experiments without constantly rerunning your experiments, right? So you do have to redecay every time, but that's maybe 10% of the total cost. It's a much better situation to be repeatedly decaying than to repeatedly rerun your pre-training runs. And this is a very common trick that's used in many places. I'll show, I guess, a performance comparison. There have been many plots of this form. I think, who was the most recent folks that were maybe it was Martin Jaggi and others, I think over at ETH, had an extensive study of WSD sort of performance. But I think a lot of papers have shown similar things of, you have a well-tuned cosine learning curve. This is, the orange line over here. And then you've got various WSD curves. And WSD curves always look a little bit funky because it looks like you're way underperforming until you hit the decay phase, where suddenly you kind of reclaim all of your gains, and then you sort of match or even sometimes exceed the cosine learning rate performance. Anecdotally, I think if you talk to a bunch of people training networks, I think a lot of people will say the cosine is slightly better in many cases, but WSD is basically as good in many other situations. It is a very versatile default learning rate, doesn't necessarily suffer from having to sort of rerun if you want to just continue runs. It is very cool, though, to see just how much of an impact learning rate decay has if you haven't played with that before. This part of decaying the learning rate is just incredibly important to sort of getting the final sort of annealing parts of your training together. Okay, so that's the comparison there. Okay, so now that we're equipped with WSD-style learning rates, chinchilla-style analyses are actually very easy. What you're going to do is you're going to, essentially run one long run, and then you'll just sort of rewind the checkpoints and then repeatedly decay. And that will give you sort of sweeps along the data dimension, and then you'll also do sweeps along the model dimension. You can do isoflops or any other kind of analysis that you would like. The mini CPM authors, for whatever reason, choose to try to replicate methods 1 and 3, which to me are the least reliable of the chinchilla methods, but they do get fairly nice looking scaling curves. If you look at the mini CPM sort of chinchilla method 1, they see nice lower envelopes that look mostly linear across these, which is good. And then method 3, they get nice smooth scaling for the most part in both sort of the compute to non-embedding parameter trade-off. So it seems like for the most part they get reasonable chinchilla-looking fits. One thing I will point out is that they get pretty different exponents for their overall joint fit compared to chinchilla. They claim in the paper that this means that they should be training with way more pieces of text than chinchilla. It is highly unclear to me whether this is really true or whether their chinchilla fits are a little bit strange relative to the original chinchilla paper. Okay, I'll stop here for one moment in case someone has questions about mini CPM. Maybe the main couple things to take away is one is the use of μp is a useful trick, I guess, to try to stabilize how your learning rate changes over scales. And then the second thing maybe to remember is the WSD learning rate. That's just a very common trick. You should all kind of know about this learning rate. That's a basic thing to know. Okay. Good. All right. So then I'll move on to DeepSeek. This is the kind of original DeepSeek paper before they started talking about MOEs and all these other sort of very cool things. And I think even at the very first DeepSeek paper, you could kind of tell that these were very serious people, because I think DeepSeek LLM, even now, is I think one of the more nicely executed scaling analyses in the open world, right? And I feel like they have lots of great taste in the experiments that they run. So even before R1 and so on came out, it was like kind of clear that these people were going places. All right. So DeepSeek takes a very different scaling strategy than mini CPM and several others in trying to optimize their hyperparameters. Like they're not going to really do μp, right? They're not going to do this like interesting scaling adjustments. Instead, they are going to try to fit a scaling law to estimate both the optimal batch size and the optimal learning rate, right? So we know that the learning rate and batch sizes should actually change with scale. But if the way in which they change are predictable, just like a scaling law, then we're good to go, right? Like we don't really need to worry about very much. So what they do is they basically run extensive grid searches at various different scales, and they try to find the optimum, right? So this is an example of the kind of thing they're doing. They're sweeping learning rates, they're sweeping batch sizes, and they're looking at sort of the terminal loss if they're processing a particular number of tokens, right? So they fix the compute, and then they vary these two. They'll do this across several different scales, and then they'll basically try to identify what the lowest loss is, so in this case the lightest color, right? So they'll put a little star there, and then they'll do this across scales. So if you do this across sufficiently many scales, you will get a plot that looks like this, right? And this plot is saying, okay, I'm going to vary my non-embedding trading flops across some range, and you can kind of see these gray dots over here, right? And I'm going to vary, as I vary this, my optimal batch size will change. Where, remember, the optimal batch size is derived by looking at these big grids and kind of finding the minimizer, right? And I will get something that kind of looks like a line, right? The optimal batch size should scale with my non-embedding flops. And similarly, for my optimal learning rate, right, I'll get a bunch of gray dots in my sort of non-embedding flops range, and then I can fit a line to that to try to estimate what my optimal learning rate should look like, right? So this is fairly nice. And I guess one thing I'll point out is, their full runs are on the star, right? These are the runs that they chose. At higher flops, they have much higher batch sizes and much lower learning rates, right? The stars are the things they actually ran for their big runs. These fits look reasonable for the batches, right? This kind of does look like a line. The one on the learning rate, I'm not quite sure that constitutes, the best linear fits that I've seen in my life. But I guess it works, so it's probably fine, right? Like the models do train, the models do get reasonable things. I think this is the one I would say like drawback of the learning rates approach. It's not really clear that if you try to do this grid search kind of thing, unless your grid is in the right place, you've got a lot of quantization error, and then you're not getting very good scaling law fits, and you end up with kind of something that looks like an arbitrary linear thing going on. Okay. Oh, yeah, sorry.
How come for the same number of training flops, there you get multiple data points with a large range of optimal learning rate?
Why is it that you get a large range of optimal learning rates for different training flops? Is that the question on the y-axis over here? Yeah. So the reason I think there is because of the changes to the model sizes and things like this. And so, 2024 was back in the era where I think every open model builder was replicating the entire scaling law stack. And so, DeepSeek also complements the, like learning rate analysis with basically a chinchilla replication. And to do that, they're also going to do the same thing as mini CPM. They're going to follow the WSD style learning rate. They have a weird little variation where they do 2 decay phases instead of 1. I am not really sure why this is. It hasn't really been a thing that has taken off afterwards, but it is a thing that they do. Regardless, the whole point here is to say WSD is an effective approach, and you can use that to replicate chinchilla. And DeepSeek, has much nicer scaling curves than mini CPM because of their choice to go with isoflops, so they get these very nice, clean sweeps across the fixed flops ranges, and then they also get fairly nice and clean chinchilla-style trade-offs as before. So this allows them to essentially replicate the chinchilla results and get a similar kind of a data model scaling law. Really, the point that I'm showing with this is just to say, look, the chinchilla laws have been replicated by other people at large-ish compute ranges, so that analysis is generally sound. Finally, I think this is kind of I'm a little bit sad that these kinds of plots are now somewhat rare in open source release papers, but this is really the final punchline of a lot of scaling law work, right? You train a bunch of small curated models, at smaller compute ranges, and then you kind of like draw out the power law, and then in the end you get something pretty close to reality if you scale out enough, right? So the 2 stars are the models that they actually trained, the gray dots are their scaling law fits, and they're getting like pretty good predictions on their star. I mean, it could be better, but it's not bad at all. And so they're able to get some pretty accurate scaling law predictions on real, open source models that they've trained. Okay, actually I'll stop here. If people have questions about the DeepSeek stuff, feel free to ask them. I think my one-line summary here is to say, this is the other approach to dealing with the sensitive hyperparameters. You can either attempt to stabilize them, or you can attempt to just scaling law fit them, right? And then just go with the scaling law. And DeepSeek, it represents the more like fit the scaling law approach to this problem. Good, okay. So there are other models, more recent ones, that have nice scaling laws that they talk about. As I said before, though, I think a lot of this work is now kind of it's kind of like all known to everybody, and so no one is really putting a lot of this stuff into like big sections into the paper. So if you look at Qwen 2.5, they say something like, okay, well, we need to tune some optimal hyperparameters like batch sizes and learning rates. So we do a bunch of scaling experiments to figure out what the optimum are, and then we have a scaling law, and we predict the optimum, and then we're able to do that even for MOEs, right? So this is basically the same thing as the DeepSeek analysis, right, that they're talking about in Qwen 2.5. Same thing with Qwen 3, right? By the time it's Qwen 3, they say, all right, we've already figured out what to do in Qwen 2.5. We're just doing exactly the same thing, right? So this has become part of a very standard recipe that you use in order to nail down the optimal learning rates and batches. Kimi K2 is probably the newest paper that I'll talk about of the series. At this point, I'm just going to quickly go through several papers, maybe to give you sort of an overview of what people are doing in terms of scaling work in the open source model releases. So Kimi K2 and a few others have focused on essentially MOE scaling laws. So it's 2026. Most people know how to do a chinchilla scaling law or even a learning rate scaling law. What things are new? Well, a lot of these companies are now switching to MOEs, fully switching to MOEs, right? And if you're doing that, you really want to know, am I training the right amount of active parameters? And so they're doing things like, okay, we're going to vary the flops and look at my losses, and I'm going to do so for different levels of sparsity so that I can figure out how much sparsity helps or hurts my losses. And their conclusion, of course, is if you look at the different sparsity levels, the more sparse your network, right, the better your validation loss given a flop. Unsurprising. But now the fact that they can quantitatively know what the relationship is between sparsity and loss means that they can make sort of more rational decisions about how much sparsity to put into their model. And they look at this and they say, okay, what we're going to do is we're going to use a sparsity of 48 because at that point we're hitting diminishing returns on our scaling laws. Right? So you can kind of see how this kind of analysis is used to justify different architectural decisions across different open source releases. Hunyuan, which is another open source MOE from a few years ago now, they do a very similar thing, right? Like I think every company, once they switch to the MOE, has to do this kind of like MOE scaling law to figure out how the number of activated parameters or the amount of sparsity changes training loss, and then they kind of redo a lot of these analyses. So for example, in Hunyuan's case, they end up with like a 96 data point per active parameter ratio. In their case, they're fixing the sparsity level, and so that's not a thing that they're searching over. Llama 3 also has some nice scaling laws. Unfortunately, they're not particularly useful ones. They do isoflop style scaling and get slightly different but similar ratios for token to model. The most interesting thing that they do in terms of scaling in Llama 3 is the plot on the right here, which is they have the usual scaling law, which is the left panel, that's saying if I have more compute, then the log prob on the sort of answer for a benchmark sort of decays consistently. And on the right side, they show, okay, well, if you have better sort of log loss, then the downstream accuracy also goes up, right? So they're basically saying, well, we can just fit a sigmoid on these purple points, and that might give us a sense of like how good these different models are. You can kind of see there's systematic deviations from the curve, so I don't really know if I would really buy that this curve is like the one truth that's going on, but you can certainly see that it is consistent with a sigmoidal scaling mapping from the loss to the accuracy, which I think is very useful, right? Because we've been talking only about kind of log losses, but there is a tight coupling in some cases, or in many cases, between log losses and downstream accuracy. Okay. And then sort of for one last paper that I want to talk about for scaling, Minimax 01 from last year had this nice set of scaling experiments where they were doing the exact kind of thing I was saying is a useful affordance of scaling from 2 lectures ago, and that is architecture variations. And so they wanted to understand, okay, I have lightning attention, which is like some kind of a linear attention architecture. I have a softmax version, like full attention, and I have a hybrid version that mixes the two. How do these things scale? Is it the case that if I scale up, one of them will get much worse than the other? And so you can kind of see they're replicating essentially the Kaplan plots of like as I increase flops, how do the learning curves change? And is the number of parameters that I need different for different levels of compute for these different architectures? And the answer is, for the most part, kind of no. That hybrid and lightning and softmax are all comparable for the most part, and they require similar model sizes. And this set of plots is used to justify their use of the hybrid architecture in the actual deploy system, right? So this is exactly the kind of decision making that you would do based upon a scaling law. Okay, so that's basically what I wanted to cover for the recent scaling law recipes from the various companies. So the 2 things, as I said before, for the DeepSeek recipe, right, really the key thing is the scaling analysis on the batch and learning rate. This is the scaling-based approach. And Mini CPM follows a more of a mu-p style approach to try to get invariances. And then we see some trends. We see that like Kimi and Quen and others and Hunyuan are doing these like MOE scaling experiments as they switch to MOEs. We see some architecture work by Minimax, and we also see some isoflops analysis being replicated by several others. And to return to a previous point, right? The point here is I think a lot of companies are now less detailed because the core scaling machinery, like doing chinchilla or doing learning rate scaling, is now fairly well understood by everybody. So there's no necessarily extra value in showing those experiments for some of these releases, or at least that's my guess for why we have much fewer of these kinds of experiments in the release. Okay. I'll take 1 minute and then sort of pause and let you digest and ask a question or two in case you have questions for this part.
Okay. So all these cover the pre-training stage. So my question is, what changes and what do not change when now post-training is kind of standardized process for all the development?
Yeah, so the question was about what changes about this when you do, or when you think about post-training, I guess, broadly. I think that's still a big open question. There's no great way to do like fully integrated scaling with like post-training accounted for, because post-training like can sometimes really change the nature of like, what pre-training you should do. The closest things that I can think of to thinking about post-training is there's been some work on like understanding like coverage or like diversity notions in pre-training that would help predict what happens in post-training, but it's still pretty nascent work. I don't think there's any good answer to the question of like what do we do about synergy with post-training. Cool. Okay. So now we're going to talk about the other piece. So I think the two remaining parts of this lecture kind of map on cleanly to the two examples. So I'm going to talk about one set of approaches, which is about scaling laws for learning rates, batch sizes, and optimizers. Right? That kind of corresponds to the DeepSeek approach to the world. And then I'm going to talk about kind of the MUPI stuff, right? Like that's kind of the mini CPM approach to the world. Can we just reparameterize everything to make it so that we don't have to worry about scale? So we're going to now talk about kind of the DeepSeek approach. How do we scale learning rate properly? And so there's going to be a hyperparameter part and an optimizer choice part. And I'm going to draw quite a bit from this pretty recent preprint from the StepFun folks. I don't think there's like a great, really, truly like reliable, robust study on hyperparameters, especially learning rates. But this is probably getting somewhat close. The StepFun folks train credible large models and release them. And they burned a ton of compute in grid searching the space of hyperparameters in this scaling law study. So I'll go through this and show you some intriguing empirical phenomena about how learning rates, batch size, and all of those affect downstream losses. Okay. So lots of people have talked about lots of different ways of scaling learning rate and batch sizes as roughly as a function of compute. And the StepFun paper, the hyperparameter tuning paper has this very nice table that captures a lot of this. And I'll point out a couple of different things. Some of this we already know. So the very top row, this OpenAI scaling law, this is from Kaplan. If you look at the batch size over there, notice how it says 2E18, capital L to the exponent. That's critical batch sizes, right? It's basically saying, you should scale your batch size as a function of your terminal loss. Great, right? DeepSeek we just saw, right? This is kind of the compute-based scaling laws for both learning rate and batch size. And there's been a couple of other folks that have proposed various kinds of scaling, including mini CPM, which we talked about as well. Another important thing that I want to point out is that these formulas for learning rate and batch sizes, they don't even have the same inputs, right? People don't even seem to agree what are the variables that should affect these learning rates. The OpenAI one is terminal loss, whereas the StepFun folks, they claim that the right batch size scaling is a function of the data. So there's a lot of different sort of disagreements about the nature of scaling for hyperparameters. And I think one thing I'll say as I go through this is not to take even this last row as kind of gospel, right? A lot of these things are pretty brittle in many ways, but the experiments and the phenomena are things that you can learn well from. So I'll do that. So the design of this paper is very similar to the DeepSeek one. They're just going to train a ton of models to grid out both the learning rate space and the batch size space and do them across a range of models and range of data set sizes. And by doing so, they hope to essentially saturate the hyperparameter space for a set of small models and then nail down what the optimum is. And much like in the DeepSeek design, they're going to be, after they grid up the space, in this case they have a contour plot, but the underlying objects are just they run a bunch of models, they aim to try to minimize sort of the losses, right? And the contour plots are quite nice. I feel like they give a good visualization. They ran a pretty high resolution grid, and thanks to that, one of the things that we can see is that they can actually plot out a fairly high resolution contour of what the hyperparameter space looks like. In this case, this is a slice at 1B parameters and 100B tokens, I believe. And you can sort of see on the right side, that surface is the hyperparameter sort of landscape. As a function of the batch size, which is kind of on one axis, and learning rate, which is the other axis, how does the loss change if you fix the total amount of data in the model? Now, we see that each slice, like if you fix a batch size or you fix a learning rate, right, each slice is kind of nice and convex, and it's almost even smooth. And this is quite nice because it means that you can, kind of search for the optimal hyperparameter, fairly nicely, and you can be confident that the minima is not too far off. If this was very jaggedy, you might have some, very serious doubts about whether this kind of program of gridding the space is even viable. Also, this should maybe give you some nice intuition about the smoothness of the hyperparameter space in general. And I think there's actually one really interesting general scaling trend. And looking at other related papers to this topic, I don't know if I've seen any contradicting evidence to this observation. So I think the one thing that seems very interesting, and one of the key takeaways of this work, is essentially if you're looking at the optimal batch size, right, the only thing that seems to depend on is the total amount of data that you're training on. So this right-hand plot is the one to look at, right? So x-axis here is the amount of data that you're training on. The different colored dots, those are different models. Notice how the different colored dots seem to follow roughly the same trend line here, fairly predictable one. And this is in log-log scale, so you should expect some sort of a power law that's a function of d, right? On the left panel, we have the dependence of learning rate, and we see that this is a very different behavior, right? Bigger models, so if you go from blue all the way to this pink color, right, bigger models have smaller optimal learning rate, and larger amounts of data have higher optimal learning rate, which is kind of counterintuitive, actually. And so this might be a little fragile. There are other kinds of papers that argue that the dependence on D should be kind of reversed, but the trends here, at least on this experiment, are quite clear. Okay. And one final thing that I kind of want to point out is the learning rates are actually pretty robust. And I think this is backed up by a lot of experiences and experiments that people have. I think people have a sense of actually as a poll, do people know what a good hyperparameter is? If you were told to train a language model tomorrow, would it be 1e - 3, 1e - 4, right? I feel like we roughly have a sense of actually this range of hyperparameters for learning rates is generally a good starting point. And that is generally true. So the scaling laws that they got, actually transfer over to, for example, MOEs to a certain extent. The yellow stars, which might be a little harder to see, are the predictions from their scaling laws. The red X's are sort of the optima that are derived sort of directly on the MOEs. And so, you switch to an MOE, you don't end up with a very different scaling law as long as you're roughly controlling for active parameters. The one thing that does seem a little bit more potentially dicey is as you shift the training data, the optimal learning rates and the optimal batch sizes do shift a little bit, right? Which means that all of these phenomena are likely contingent, the specific numbers that are in these scaling laws and so on are potentially contingent to the data that you train on more so than others. And so I want to flash this back up before I sort of move on. Right, so you end up with some sort of simple scaling law at the end, which says, okay, batch size, maybe should be roughly square root of the number of data times some constant. Your learning rate should kind of scale, upwards with batch size or upwards with data, but downwards with the model size. And that's kind of a surprising effect, but not maybe crazy because these experiments often, in many cases, are assuming chinchilla-like scaling, in which case those two would kind of cancel, and as you increase compute, your learning rate should go down, right? Hopefully that chinchilla comment was clear. What I mean is when you're scaling by chinchilla, N and D are sort of both driven by compute, and as compute goes up, you expect your learning rate to go down, right? And so you will end up with something like the DeepSeek law, where the learning rate decreases with compute and the batch size increases with compute, albeit with different exponents than the DeepSeek law. Cool. Okay. So in some sense, this is the newest and most large-scale version of the DeepSeek analysis. And this is one way that if you were doing the scaling law style approach, you would approach this problem of fitting a learning rate. Okay. So that's the hyperparameter story. If someone has questions, feel free to stop me. And then next, right after, I'm going to move on to talking about optimizers. I think this is one thing that I didn't have time to talk about in the architectures lecture. That was already a pretty packed lecture. But I think it would be sort of a disservice to you if I don't talk about optimizers. And optimizers are scale dependent, so this is a good place to put them and talk about some of the latest and greatest developments in optimizers and their relationship with scale. Oh, yeah.
So I guess I'm trying to figure out how to interpret this. Does that mean we should just take the scaling laws that we have and then apply them rather than running our own grid search?
Yeah, I mean, I think it depends what regime you're in. The question is oh, sorry, I have to repeat it for the online folks, right? Is, should we just take the scaling law and run them, or should we just do our own grid search? It does kind of depend on the amount of compute budget that you have and how much you need to nail it. I do think, for example, maybe the step fun law, if you're in the right compute regime, close to where they were running the grid, these are probably really good defaults, right? I would bet on these over something I pull out of my hat. That said, if you were doing your own big pre-training run, you are probably going to have minor differences, right? Someone might say, I really believe we should have a big weight decay. My architecture has a big weight decay. We don't know necessarily that those things are going to scale the same, right? And so you might want to actually redo a lot of this. And this is why I think a lot of the reports I showed you were redoing chinchilla, redoing all these things, because there's enough minor differences that people want to check and make sure that they're roughly first order correct with these results. I think this will come up again in this next optimizer part, and I was talking about this with earlier, which is, scaling laws kind of have this very scientific feel to them. It's oh yes, fit these lines and extrapolate them. But ultimately, a big part of scaling laws is still vibes, right? It's do I really believe that the experiment setting of this step fun survey is similar enough to mine that they will transfer? We can't possibly know, right? There are always tiny differences. Good. Okay, so now I get to talk about optimizers. And I think there's been some really exciting developments in LLM optimizers and maybe even deep learning optimizers in general over the past year or two. And so this is an exciting time to talk about them. And so kind of the story that I want to start with, and one that should maybe motivate this subsection, is this comparison over here. Or maybe we'll start on this left panel, right? So this is from NanoGPT Speedrun, which inspired our assignment 1. And there, you have a really teeny tiny model that you're training on a fairly short amount of time. And you want to get to, I forget, 3-point some loss as quickly as possible, right? And many people have been hill climbing on this benchmark. And I think one of the more remarkable things that have happened on the benchmark is as a benchmark called Muon, in purple over here, came and got really significant gains over Atom, which is blue. It's right underneath the green line over there. So you can just look at the green and the purple and that gap, and you say, wow, lots of big gains from just changing the optimizer to this Muon thing. And it's not even slower than Atom, much slower than Atom. That's great, right? But then there's a question of well, is this thing actually good at scale? And then you go and run some scaling studies, and maybe they're not quite as good. This is a really tricky and important part of how we do research, right? We have a small scale experiment. We have something that's scale dependent for sure, like an optimizer. And then we see really big gains in the small scale. What do we do about the large scale? And more than providing a solid concrete prescription, I want us to maybe almost even provide a story here so that you can kind of get a sense of what we can do and what things we can't necessarily know. Okay, so actually, before I move on to the next slide, and this kind of thing happens all the time, where you come up with a great thing small scale, and it just doesn't maybe pan out large scale. So what's the difference? I'm going to spend a few slides talking about Kaiyue and sort of Teng Yu and Percy and David's paper on basically doing a large scale set of experiments on comparing optimizers and trying to do that comparison better. And there's a lot to learn about scaling and other things from that, but also just standard deep learning stuff. There's really basic things like the hyperparameters for different models are different. So if you're scaling things up, maybe they even have different scaling exponents. So you have to tune Atom really well. So if you tune it badly, you get this darker brown line, and you're like, wow, this thing is much worse than all these other algorithms that I have over here on the left. But then you change the learning rate a little bit, and you're like, wow, actually all my gains went away. Similarly, on the right, you can have cases where maybe you've tuned your learning rate well, but now you've got other stuff like weight decay that is not optimally tuned. And so if you use the same weight decay, then you're certainly going to get a much worse result for this green line, right? If you pick this small weight decay, you'll get a much worse result for this green line than if you pick the optimal weight decay, right? So there's all sorts of pretty tricky things going on. Technically not a scaling thing, but a very important general empirical machine learning thing that I want to point out. But maybe more relevant to the discussion in this class right now is the scale dependence of these things. And I think this is a good sort of case study and example of how to really think about algorithm development as a function of scale. Because to me, there are two variables that are always important when thinking about scale. And this paper exposes, to most extent, both of them. So one axis is compute. And if you're fixing the if you're fixing the model size to data ratio, like the two are coupled together, then this is essentially a compute axis on the x-axis here, right? So you always want to, whenever you're doing a study, essentially scale up the compute and look at the trends as a function of scale. And we see right here that if we look at the relative speed up between Atom, which is at 1.0 by definition, and all these other alternatives, we see that muon's really good at small scale, and that gain sort of diminishes down as we increase in scale. That's not really necessarily the picture that you want to see. There's another axis that you should always be vigilant of if you're doing algorithm development. And the other one that you should be vigilant of is the chinchilla ratio. So the chinchilla ratio can be thought of, it is the ratio between how much data you have and the amount of model you have, right? And this is a really, really, really important parameter because some algorithms work well in kind of the over-parameterized case where you have a way bigger model than you have lots of data, right? Maybe your algorithm adds some implicit regularization, right? Or maybe it is data inefficient, but it works well because of compute reasons, right? So some algorithms might work well at the small chinchilla ratio case. In contrast, other algorithms might work well in the large chinchilla ratio case, where you have lots of data per unit parameter, right? Because you can pack knowledge more efficiently into the parameters, right? So this is a big, big, big confounder. Even papers that I think have pretty good hygiene in doing scaling experiments on the model size axis often neglect to or just don't have the compute to sort of study the chinchilla sort of token to parameter ratio, and this turns out to be surprisingly important a lot of time. In this case, it's not. In this case, you see that the optimizer sort of gains are pretty consistent. The ratios between all the lines are the same at different chinchilla ratios, but this is not always the case. You always want to be vigilant about both of these scaling factors. That's quite important. And then I'm going to also point out, if you have a new algorithm or a new setting, right, establishing scaling is quite non-trivial, right? So I've taken this from one of Will Held, who was working with Marin, which was Percy's open source language model training project. And there, they were basically trying to prove out a particular set of hyperparameters. This isn't even like a new algorithm. So this is cautious atom C, which is like an atom variant, square root batch size scaling, and a bunch of other sort of standard looking things. And they're doing essentially the same sort of chinchilla analysis that you've seen all the other papers do. But because this is not necessarily a paper, this is a bunch of people doing experiments, you don't just publish the successful one. They have the niceness of publishing their failed runs. And the example here is that they're doing basically standard chinchilla stuff. And it's looking great. If you go up to this dashed vertical line at 10 to the 20 something, this is a really beautiful looking scaling law up to here. And then as you scale up, it's like, well, it gets a little bit worse. It's a lot worse. And then wow, now that run is not so good anymore, right? So it's totally blown up on you. And the point here is that even good looking scaling trends for many orders of magnitude can suddenly kind of bite you, right? Like it can deviate from linear, and then it can then kind of blow up immediately. And in their case, the fix here is just picking more careful mu-p style parameterizations, optimizer changes. They switch to a different kind of optimizer, and they get nicer scaling across more orders of magnitude. But the point here is to say, when I go back here and I say, okay, well, you should all do scaling experiments. You should scale all your learning rates and so on. That's not easy, right? You end up fairly non-trivial fraction of the time with plots that look like this, and it's all kind of horrible, and you're not quite sure what has gone wrong. Good. Okay. And then so the last thing I want to end with is just talking a little bit about muon and sort of the closing up the muon story. So I feel like I have to talk about muon in a little bit more detail than I already have, just because it's beginning to be integrated into large-scale model training runs. That's kind of the inclusion criteria for a lot of new research topics for the class. Has it been in a big training run? And muon now checks that mark. And it's also just kind of an interesting algorithm. So I'll mention it and talk about it for a few minutes and then move on. So in gradient descent, we usually have a fairly simple thing that's happening. Ignore line 4 for the moment, or sorry, line 5 for the moment. And then you're going to get roughly a standard momentum-based optimizer, right? I take a gradient, I add it to b of t. This is my momentum step, right? So I continue my momentum from before with parameter mu, and then I update my parameters based on this momentum gradient. Very standard, momentum gradient stuff. But then I think the really interesting, and to me at least, a bit of an out-of-the-box set of ideas is to say, well, gradients have this property that they treat all the parameters are the same. But we know that not all the parameters in a language model or even a deep neural network are the same. Some parameters are like vector parameters, like they belong to the RMS norm. Some parameters are matrix parameters, like for the attention or for MLPs, right? And matrix parameters are probably different than vector parameters. And so that's kind of the starting point for this idea, and I think a really interesting one. And so the one thing that you could do about matrix parameters is you can start to look at their spectra, right? Like they are matrices. Matrices have eigenvalues and singular values. And so you can do things to the singular values. And so what you do here in muon is this fairly simple idea. You compute a gradient, you take a momentum step, and now I take my update b of t, and instead of directly applying it to my parameters in line 6, what I'm going to do is I'm going to do this Newton-Schultz thing, Newton-Schultz 5 to be specific. And what that is it's going to orthogonalize the b of t matrix. And so I've written the operation down there on the bottom. Let's say I take b of t, I write it as singular value decomposition, u s v transpose, and then I make all of my singular values 1. Right? So if my singular values are really big, I'll shrink them back to unit. If they're really small, I'll expand them back up to being unit. And then I take UV transpose, and that's my new update that I'm going to apply. Right? If you want intuition for this, and you already have intuition for something like Adagrad or these other, or Atom even, in Adagrad or Atom, you're going to divide by kind of the size of the gradient. Right? So every coordinate is roughly going to be the same size. In muon, you are operating in the spectral norm instead, so every kind of direction is going to be unit size, right? And notice that this only makes sense for a matrix. I can only define this notion of a singular value decomposition for a matrix valued b of t, right? So the interesting thing about muon is it's a matrix optimizer. So you apply it to these matrix valued parameters, and for the vector valued ones, you might still use something like Atom W, right? Because those don't really have any sort of interaction with the Newton-Schultz term. Oh, also, Newton-Schultz is an approximation to that operation that only uses matrix multiplies, right? So it's systems efficient and not exactly the orthogonalization. But okay, like why have I spent all this time talking about muon? Well, first of all, it's very powerful for things like the NanoGPT speedrun. It was discovered for this set of things, and so you might think that it works well. As I said in the previous slide, there have been some scaling studies that have argued that the gain for muon sort of decreases as scale goes up. But then, I kind of want to close off this story, which, I think initially this came out, and I was like, wow, muon's kind of interesting. I wonder if anyone will scale it up. And then Kaiya and others scaled up muon, and they said, well, maybe it doesn't work super well. And I thought the story was kind of closed here. I was like, well, maybe this is done. No one will spend the big compute to scale this guy up to the full pre-training size. And then Kimi K2 comes out, and that whole model is trained with muon, like fully with muon, with a few bells and whistles to prevent muon from like blowing up on you. They found a whole bunch of instability issues. But Kimi K2 is an outstandingly good model, right? Like it's a very good model, and the training curves look, reasonable. And so really what this suggests is like, well, muon worked at scale. Like, is it better than Atom? Kimi K2 certainly doesn't have any ablation, so we don't know at that scale. But it is certainly a valid and workable solution. And so what's the point of this story? It's to say it's really hard to know whether something works at scale. It's very, very hard. But thus far, a lot of like small scale experiments and transferring them up to large scale has been the way by which we do science, right? And so, you still want to respect things like the nano GPT speedrun. We learn quite a bit from that and get good ideas, and then eventually they make their way to the big models. We'll see if, people continue to do ablations at big scale and really nail down, is muon better than atom W at scale and so on. Those are interesting questions to which we don't yet have the answers. Okay. I'll pause here for a moment. This is the end of my optimizer section. I want to make sure everyone's good. Also, especially because I was talking about muon, and that's a whole new can of worms that I haven't talked about much before. Yeah?
Is the synchro letter decomposition stack faster on GPU?
Okay. Great. Yeah, the question was, is the SVD fast on GPUs? SVD is not fast on GPUs, but they're not doing SVD. What they're doing is Newton-Schultz. Newton-Schultz is a matrix multiply only finite iteration algorithm that approximates the process of orthogonalizing a matrix. So there's like kind of several clever pieces here. One of them is kind of the idea of like treating it as a matrix on its own. And then there's this orthogonalization idea. And then there's the systems piece of doing it with Newton-Schultz. So those are all like important, interesting pieces. Yeah, back there.
Are the hyperparameters for atoms for the vector ones?
Are the hyperparameters shared? No, they're different. Yeah. I think there are several people that have been working on this like muon style line of work. And one of them, I think, like Jeremy Bernstein, I think he's been saying like actually like every layer should have its own learning rate. I think the ultimate limit of this is like you go from, or even like every layer should have its own optimizer, right? The ultimate limit of this is to say every parameter in a transformer is different. Why not have a different optimizer for each one of them, right? And so you would have to tune hyperparameters for each one of them as well, which I do not want to do, but that's maybe the future of optimization. Yes.
What's the validity of like for on the learning rate and batch size, like they just consider like these two things, and then you pick the best out of those, and then you kind of use it to tune other things. But do these things like interact with each other?
Yeah, or maybe the version of the question that I interpreted was, a lot of these people are just tuning learning rate and batch size, and they do this on the grid. But presumably these things interact with a whole bunch of other hyperparameters. Aren't you worried about that? And I think in general, yes, you are worried about hyperparameter interactions. But realistically, they grow exponentially, right? Like this is not a thing where you can grid out the whole space. And so I think the thing that people often do is they grid the stuff that's most concerning and most sensitive. And learning rates are very important. I think if you've ever tuned stuff, learning rates are the most important thing to tune. So they very aggressively go on that. And then stuff like weight decay, they might do a univariate sweep afterwards, right, to be locally optimal with respect to those parameters. Good. Okay. All right. So the final part of this lecture is I want to talk about μ-p. μ-p is a bit of a mysterious object. Even with many papers written about it and sort of, in fact, even many implementations, I don't think all of them even agree on what the underlying math is or what the underlying implementation should be. But there's a core set of ideas that are shared, and it does seem generally effective. And so I'll talk about my interpretation of the whole program, let's call it. So the goal, hopefully, is very clear, and I think this picture is the goal. The picture being, well, if we increase the size of our model, in this case just width, our optimal learning rate normally shifts, but ideally, we want the optimal learning rate to be the same no matter what. Right? That is the game that we would like to play, and the knobs that I'm willing to tune to do this is I'm willing to mess with the initializations at a per layer basis. I'm willing to mess with the learning rates on a per parameter basis as well. And then I'm sometimes willing to scale up or down things like residual connections, right, based on the size of my model. Okay, so that's the game that I'd like to play. And how well does it work in practice? There's been several papers that have studied these fairly extensively. Cerebras, which is really a chip company, also has a language model training arm run by Hessness of the scaling law paper fame. And they actually, I feel like they do very interesting things because they now are writing lots of papers about μ-p scaling of language models. And they have Cerebras GPT from a couple of years ago where they were training the 0.1 to 13b models using the usual chinchilla recipe, but also including a μ-p variant, which they use to try to tune the hyperparameters more effectively. And I think one of the nice things about this is they find that if they use the μ-p parameterization, then their scaling law fits are generally more stable. Their projected mu-p trends are almost right on the money for their actual models, whereas I think their non-mu-p models sort of fluctuated much more wildly in terms of the loss predictions that they had. And so their claim was, okay, mu-p is maybe a really good idea. So this is validated at scale. You saw mini CPM and others. Many people have trained models with mu-p variance. So I could also talk a lot about training or examples of models trained with mu-p, but I think maybe the more interesting thing for me to do right now is actually to talk about the conceptual foundations and the math, sort of, for mu-p. And if you're interested in this and you want to read a somewhat accessible paper, I would recommend this one. This is the paper that I think, for me, was the clearest. There are several papers. Greg Yang, who kind of started this research program, has a series of papers called Tensor Programs. I find them somewhat inscrutable. Jeremy Bernstein, who was also working on the muon stuff, has written this nice sort of, not recap paper, like a review paper, sort of putting it into a different framework, which I think is very accessible. And there are several others by physicists that are also interesting in terms of explaining what mu-p is. The Cerebrus people actually do a bit of that as well. Okay. But anyway, returning to this paper, the core idea of mu-p is based off of two kind of assertions, right? And this is a very physicist way of thinking about this. So if I make my network big, let's say I'm only changing the width for now, right? I'm making the width of my network big. I'm going to assert two invariants that should hold as I do the scaling limit. First of all, the activations at initialization, so if I initialize my model and I put in some random data, the activations should remain the same size roughly as a function of the network, right? So if they blow up with the network size or they shrink to 0 with the network size, I have chosen a wrong parameterization. And that kind of makes sense, right? My activation should be roughly the same scale regardless of the size of my network. Now, after one gradient step, the change in my activation should be O of 1, right? So this is what people call feature learning. So feature learning means if I take a gradient step, things in my network change a significant amount. And that this amount should be a fixed function of the width of the network. In case some of you are theorists, right? You might be familiar with neural tangent kernels. Neural tangent kernels would have a very different behavior. Those would be the kinds of things where the change in activations actually vanish as a function of the network width. And you don't want that because you do want the network to change and learn features and do things even in the limit of your big sort of neural networks. Okay, so these two are the invariants. They kind of make sense. They're basically saying activations and the change in the activations should remain roughly similar as a function of the width of the network. And then note that I'm going to sometimes go back and forth between individual activations, which is this, and then the norm, which if each activation is roughly O of 1, the norm of the whole vector or of activation should be square root of the number of hidden units in that layer. Okay, so that's the main thing. Now the thing about mu-p is it's kind of interesting because it starts with this very simple and palatable set of assumptions. You might all agree that this is a reasonable thing to do. And then we're going to make a number of additional strong assumptions. But then in the end, we're going to get a very simple set of scaling rules that drop out of this. So remember, what we want to do is we want to make sure that the activations at init are roughly unit. So what do? Well, if we have a simple deep linear network, and we initialize all of our weights as a sigma squared, scaled Gaussian, then what is going to be kind of the spectral norm of this matrix? Well, you can write that down, right? I'm not going to ask you to verify that, but that's standard matrix concentration arguments for the operator norm of a random Gaussian matrix. And then now note that in certain regimes where the fan out is, I think, not much bigger than the fan in, you're going to get that the output of the layer is kind of similar to the product of the input of the layer times the operator norm, right? This is always an upper bound, but this is approximate in certain high dimensional regimes. Now, if this is true, now what can we do? Well, we can solve for sigma to try to keep our activations the same across all of the layers and across all the width. So imagine that at L minus 1, I have sort of square root of L minus 1 activation. And this is, remember, consistent with this notation that, at least for this whole vector, I should have square root of n of L, right? So this is our base case for our induction. And then our inductive case says, well, remember that I have this operator norm at layer L, which is this function of the fan in and the fan out. And so this is going to be equal to this, if I pick a particular sigma, so let's say this is the ansatz, I'm going to assume that this is the answer, and then we'll see what happens to the induction. If I pick this as a hypothesis and I plug this into the sigma, notice that I get that the ratio of the operator norm is this, the ratio of the fan out over the, square root of the fan out over the square root of the fan in, and then I plug this back in here, and then I'm going to get that the norm of the output is going to be equal to the square root of the number of units in my layer, plus some lower order terms that I'm not going to bother to keep track of, right? So, where this sigma came out of, I mean, this is, drawing it out of a hat, but we can kind of verify that if I, plug this sort of noise initialization into my formula, then essentially at every layer, the size of my activations is roughly equal to the square root of the number of hidden units at that layer, right? There are some assumptions made here, like this approximate equals, but this is like mostly a legitimate set of assumptions. So condition A1 is pretty simple. Condition A2 is a little bit hairier, to be honest. So really, we need to deal with the updates now. And I'm only going to consider the case of a single example in a batch for SGD for linear neural network, so deep linear network. So what is this going to look like? Well, the change in my weights for a particular layer L, if you think about how this is going to behave, it's going to be a rank 1 update between my gradient for the loss and sort of the activations, right? This is true, just because of the behavior of the backwards, right? The forwards is a rank 1 multiplication. The backwards is going to be a rank 1 outer product. So now, this is the change in the weights. And now what is the change in the activations at that layer? Well, the change in the activations, I just take h equals w times hl minus 1, and I expand this out, right? And I expand this out into this formula. This is going to be exactly the change in the activation at layer L, and it's going to have two terms. One that is sort of the direct term from changes in the activation at L minus 1, and the cross term in some sense of what happens because my weights have changed, not just because the activations at the previous layer have changed, right? So there's two terms to this update. And so this is kind of the change in the activation at layer L. And now what I'm going to do is I'm going to look through each of these three terms. I want each of these three terms to have the same order of magnitude, and I want that order of magnitude to be square root of n of L. Why is that? Remember that, if I go back 2 slides, the condition that I want for A2 is that after one gradient step, the change in activation should be O of 1 or omega of 1. And so if I want that to be true, then the norm of that layer should be square root of NL. And so to do that, what I want is for each of these three terms to have that order of magnitude. And if that's true and there's no cancellations, then this is going to be the right order of magnitude. You can kind of see the sketchy pieces adding up, right? We're assuming things like no cancellations and so on. But this is giving us some interesting ways of thinking about the magnitude of each of these objects. So at this point, the right way to think about this is not like, okay, Tatsu is sitting here doing like rigorous mathematics. What I am doing here is I'm basically keeping track of all of the orders of magnitude of all the terms. And I am saying that, given our assumptions, how big should these roughly be? It's like kind of physicist math. No offense to physicists. This was developed by physicists in this way. Okay. Okay. So now, really, go back 1 slide just to make all this clear. So the first term, this comes by almost assumption, right? It's kind of the inductive assumption. We assume that delta h of L minus 1 has the right order of magnitude, right? So this comes for free. These other two terms, these are trickier. We have these terms that multiply the change in my weights in operator norm times square root of L minus 1. And so because these two are the sort of order of magnitudes of both of these terms, we kind of know how big this delta L needs to be, right? We can solve for this because we know that this left-hand side needs to be square root NL, and then we have this term, so we solve for this operator norm, and that's exactly this quantity, right? So this is going to be the goal for the next slide. I want to try to figure out what kinds of learning rates are going to give me an update that's roughly scaled as the square root of the fan out over the square root of the fan in. Right, so that's the goal, right? As I said, after I pick a learning rate, this should roughly be true. So how can we do that? Well, we're going to make yet another assumption. And this is probably the least palatable of the assumptions in my opinion, which is that we're going to assume that the loss update is going to be scaled by unit. In other words, we're going to assume that our model is actually making some appreciable non-trivial progress as a function of scale, and that that's roughly similar. not quite sure that's palatable to me, but that is yet another assumption. So we throw that down. But now the point of this assumption is that if this is true, the rest of the math works out quite cleanly. Because the change in the loss is the product of my gradient plus how much my weights change. This is Taylor approximation. And then, because this is rank 1, I can rewrite this thing as a Frobenius norm and as an operator norm. And so this right-hand side now allows us to get what we want. This is O of 1. This term we want to be square root NL over square root L minus 1. That's this term on the right here. And then finally, I have this gradient of L term. And this is going to be square root of NL minus 1 over square root NL. And then so now what eta do I need? Well, the eta that I need is going to be solving for this quantity, which is the ratio of these two guys, which is NL over NL minus 1. Right? So we made this one assumption that the left-hand side of this is O of 1, and then we've solved for all the quantities, and we've ended up with a fan-out over fan-in ratio for a learning rate for a layer. For one side note that I'll make is that for Atom, because of kind of the changes in some of this, you're going to get like a 1 over NL minus 1 scaling, which I'll mention here. Okay. So I've walked through a bunch of kind of hopefully intuitive-looking scaling arguments for various components. But in the end, maybe you are interested in like, what does this mean? What does this do for me? What this means is that we're going to change how we set our initializations and learning rates a little bit. So our initialization is going to look like, so for mu p, the blue box is kind of what we do. Our initialization is going to be 1 over square root NL minus 1 times a component that is 1 over the square root fan out over fan in. So if this is 1, then this is equivalent to the usual initialization. This is the standard parameterization. But if this ratio is not smaller than 1, then you get basically something different. You get something that's closer to the square root fan out over fan in. The learning rate, normally you would set to be a constant as a function of your model size, but you would want to set this to the ratio of fan out and fan in. And maybe more interestingly, for Atom, this whole thing is a little bit more different. I'm not going to even touch the derivation for that, where you drop this 1 over NL term, and you get 1 over the fan in as kind of the layer-specific learning rate. And so basically, layers that have big fan-ins for Atom get smaller learning rates. It allows you to have these layer-adaptive learning rates that are quite interesting. Okay. So that was kind of the derivation of mu p. Maybe, I went through a lot of details, so I do want to maybe talk about what the high-level point of that was. And the high-level point of that is mu p as sort of an argument is very interesting. Not only is there like actual useful stuff, the way in which you get to the algorithm is itself interesting. Because it's this very different kind of math in which you're saying, okay, I'm going to take a scaling limit of my network, and then I assert some invariance about my network, and then I'm going to make additional assumptions, and then I'm going to try to figure out what the constraints on my sort of hyperparameters are. And the constraints essentially give you certain kinds of scaling limits on your hyperparameters as well. Right? So this is a general principle for coming up with different kinds of algorithms or hyperparameter scalings, I think which are probably very different than what you're used to in CS or ML training. So, okay. That was the mu p derivation. I want to close out on the mu p part with just a few like empirical things. There's an interesting paper by an independent researcher on basically stress testing mu p in lots of different ways. And mu p can be thought of as a procedure for tuning hyperparameters. And so, depending on how you do things, like, Atom is going to have a certain learning rate as a function of different components of the network. So you have an embedding parameter, attention parameters, input-output MLPs, or softmax linears. All of those are going to have different kinds of scalings under mu p, as well as not mu p scaling rules. And the interesting thing here is that particular paper replicated a bunch of the mu p results for language models trained at different scales. And maybe unsurprisingly, he found almost the headline result from mini-CPM and others, which is that if you get the mu p right and you're only scaling with, in this case in a very controlled way, you get exactly the learning rate optimality invariance that baseline mu p, or just looking at kind of a variant of mu p that sort of tracks projection biases for attention, both of those transfer very nicely. But then you might ask, basically, there's a lot of things in the real world that mu p does not handle, right? Like, technically, Swiglu does not fit into mu p. Neither does variations in initialization or RMS norm, or if you really mess with your optimizer, that will mess that up too. And so you might ask, like, which of these things that are not allowed by the theory really break mu-p? And actually, for the most part, these mostly work with mu-p. But some of the things that don't work is if you learn the gain term in RMS norm. This turns out to break mu-p. Although these can be removed in many cases without necessarily hurting you, and so maybe it's not such a bad idea. But this does seem to break mu-p. It also seems to break if you use more exotic optimizers like Liang, which basically rely on the sign of the gradient. And sign gradient is kind of like spiritually similar to muon and other ideas. And so there might be other interesting things that break with mu-p as well. Finally, the thing that seems most concerning is that if you do large decoupled weight decay, you end up with significant mu-p failure. So this is maybe the one stress test that it does fail. But to close out this final section, you might, in the end, ask, like, is mu-p useful? And if you really want to stabilize your learning rates, it is actually pretty useful. There's a lot of experiments of this form where, if you increase the width, your optimal learning rate shifts very predictably, but very greatly as a function of scale, whereas with mu-p it doesn't. And so it's one of the many tools in the toolkit to try to control hyperparameter drift as a function of scale. I think it's an interesting open area of research. It's not really sort of done and dusted, and like this is the one right thing to do. But there's a lot of promise in the sort of the mu-p style initialization program. There's also a lot of promise in just fitting scaling laws as well. Okay, so final thing I want to close with, scaling in the wild is very tricky. As I sort of mentioned in one of my replies, I think the initial presentation of scaling laws makes it sound like a science, right? Like it's like, yes, draw this line, do these procedures, and you will know for sure what will happen at scale. But I think in reality, it's a lot more messy and a lot more unknown than that. There are lots of things that people do use and practice scaling laws for, like picking architectures, picking optimizers, picking hyperparameters, right? All of these things are things that people do with scaling laws. But there is really an art to it in the sense of you don't really know if it's truly going to extrapolate forever. You want to do sort of reasonable things to maximize the chances of success, right? And so there's lots of solutions that people have. You can use mu-p, you can search for the optimal learning rate, and all of these other kinds of things. And these are ways of controlling hyperparameter drift. But there's no silver bullet yet. Maybe next year there will be a module that's like, we solved it, but not quite yet. Great. Thanks a lot. I can take questions afterwards.